Okay, hello everybody, welcome to another of the tutorials regarding circular motion. This is the last one in this particular series, and we're going to look at the issues surrounding solving problems when the circular motion actually occurs in a vertical plane as opposed to the horizontal ones we've been looking at. Okay, so there's some slightly different quirks with this one. But just to get you going, here's a little scenario. So imagine a mass being rotated on a string in a vertical plane. So at the top of that circle, it's got a mass of 0.5 kilograms. It's going at a tangential or linear speed of 4 meters per second, and the radius of the circle is 0.5 meters. And what I'd like you to do is just pause the video for a second, okay, and see if you can calculate the tension in that string. So just pause it for a second, we'll come back and see how we got on. Right, okay, so I wonder if anybody noticed a little bit of a trick in this particular question. Okay, now hopefully you started off with the sensible place, which is think, right, this is a circular motion question. What do I know about forces in circular motion? Well, there's a resultant force towards the centre of the circle called the centripetal force or centripetal force, and that is given by mv squared over r, or m omega squared r, depending on what you've been given in the question. And in the question we can see we've been given the linear speed v, so we're going to use this variation. So mv squared over r is equal to mass 0.5, velocity of 4 squared divided by the radius, which is 0.5. So I've picked quite easy numbers, and that's going to give us clearly a centripetal force of 16 newtons. Now there is a trick with this question because we weren't asked for the centripetal force, and in all the horizontal force ones we looked at, that would have been enough. Working out centripetal force, that would have been provided by the tension in the string. However, if we consider this scenario a little bit more closely, you'll think, well, hang on, there is another force acting here other than the tension. So the centripetal force isn't exclusively being provided by the tension. There's another force at play, and that, of course, is the weight. Okay, so in that case, the weight and the tension both acting down. So we actually need to consider the weight here, how much that is contributing to the centripetal force, which remember is just the resultant. So if we do that and go, right, so weight is mass times gravitational field strength, which is, mass was 0.5, g is 9.81, we'll just use 9.8 for now, just keep the numbers relatively straightforward, and that's 4.9 newtons. Now our tension, okay, has got to provide some of the centripetal force, but not all of it. Because the tension and the weight are in the same direction, the weight is providing 4.9 newtons of this. So out of that 16 newtons, only 11.1 newtons, the remainder, has to be provided by the tension. So the tension is simply going to be 16 minus the 4.9, which is 11.1 newtons. So the trick with the vertical plane questions, and it really is the only trick, there's just some scenarios now to look at, is just to bear in mind the effect weight plays on it. Now on the larger diagram on the left, I'm going to leave this one up throughout there so that you can refer back to it whenever we're looking at future problems. What I'm going to do is just label this one up, and I'm going to use the same colour coding that I've done there. Okay, so we look here, we've got a mass going round. Okay, we're not going to use numbers here, we're just going to keep it generic. We've got a mass moving round clockwise this particular circle, and we've got the linear velocities marked on, the radius there in the centre, but for every position we've got a resultant force of mv squared over r that must be acting towards the centre to maintain circular motion. We've got mv squared over r at every position. However, if we consider the top, like we've just done, that is made up of two different components. Okay, we've got the tension and we've got the weight. So at the top, mv squared over r is the tension plus mg. At the bottom, we've actually got a slightly different scenario. We've still got tension towards the centre, but our weight now actually is acting downwards. Just about got that on, haven't I? Good. Okay, so we've got to bear in mind that here, mv squared over r is going to be the tension which is in the same direction minus the weight, because that's acting in the opposite direction. Okay, and that's important to bear in mind. And what you'll quite clearly see from that is that means the tension is going to have to vary throughout this cycle. Here, it doesn't have to be so large because the weight helps it. Here, it has to be quite large because the weight's acting against it. So it's got to overcome that and provide the centripetal force. And that has a couple of effects in two different contexts we're going to look at. At the side, okay, we do still have weight in both scenarios, but it still just acts down. So that's not actually contributing to the centripetal force at all, only the tension does that. Now there's a little bit more to add to that later on, but only the tension is acting towards the centre. So we've got to consider scenarios now where our tension is actually changing, okay? And furthermore, for our simple mass on a string problem, it becomes a little bit more tricky than just that. Because think about what's actually happening here. At the top, I'm just going to move that one out of the way and change. So at the top, our mass has some kinetic energy. So that's a half times the mass times the velocity at the top squared. At the bottom, it also has some kinetic energy, which is half times the mass times the speed at the bottom squared. However, between the top and the bottom, it will have lost some gravitational potential energy. Okay, so energy has moved from its gravitational potential store, and it's been transferred into, we would assume, the kinetic energy store. So that would actually equal the kinetic energy at the top plus this change in gravitational potential energy. Okay, and if we start to look at that as one thing, what you'll realise, hopefully quite quickly, is therefore the speed must change. And if you actually look at the scenario without doing any of the equations, just look at it, that will make some sense. Because as this moves around, if you particularly consider the side points here, we've got the centripetal force towards the centre, surrounded by the tension, keeping it in circular motion, that's fine. But we also have, not contributing to the circular motion, another unbalanced force downwards, the weight, that's acting in the same direction as the velocity. It's an accelerating force. So as this moves down, it's actually going to speed up. As gravitational potential energy is converted to kinetic energy, it's going to speed up. Okay, so what we haven't got in our case of a mass on a string is the uniform motion we've been looking at previously. We've actually got speeds changing as they move around the circle, which means the angular speed will also change as the object moves around the circle. Now, a little later on, we will have a look at some uniform cases. It does exist. It doesn't mean that this is just for this particular example. So we will come back to looking at uniform motion, but there's a couple of extra things to think about with the forces there. But we're just going to stick with this for now and look at what this means. Okay, so if I put those together, okay, we can see that the kinetic energy at the bottom is given, so that's half times the mass times the velocity at the bottom squared is equal to the kinetic energy at the top plus the change in gravitational. So I'm just going to write that out as a simple conservation of energy. So I've got half mv bottom squared equals half mv top squared plus mg delta h. So I'll just put that all on one line. You can see the masses cancel, and I'm going to multiply through by 2 to get rid of these halves. So I've got the velocity at the bottom squared equals the velocity at the top squared plus 2g delta h. And delta h, remember, is just twice the radius. Okay, because it started up there and it's finished down there, so it's got to do a whole diameter. Okay, now we can use our example here. Okay, if we go back to our example, we had velocity at the top was 4 meters per second, and our height would be 1 meter. It was a 0.5 meter radius circle, so the change in height would be a full meter. And we can easily substitute in some numbers here to work out what the velocity at the bottom would be in this scenario. So velocity at the bottom squared will be 4 squared plus 2 times 9.8 times 1, which is 16 plus 19.6, which is 35.6. So velocity at the bottom is the square root of 35.6. That's pretty close to 36, so let's just round it up and call that 6 meters per second. So what we've actually done in this scenario is accelerated from 4 meters per second at the top, and this is just linear speed, to 6 meters per second at the bottom. We've not got uniform motion for our mass on the string in a vertical circle, so bear that in mind. Okay, now we're going to have a little look at what that means for the tension in this string. So for the tension in the string, okay, now we have already established that the tension at the top was 11.1 newtons. That was from our earlier example. At the bottom, we've got mv squared over r equals T minus mg. Okay, so we're just going to write that out. mv squared over r equals T minus mg. So T is mv squared over r plus mg. Easy enough. mv squared over r is now the mass, which is 0.5, times the velocity that we just worked out was 6. Okay, it was 6, well, we can use the actual number, it was 35.6 for the velocity squared, so we can just put that straight in. Velocity squared was 35.6, so that we don't have my approximation error there, and the radius is 0.5, and mg is, as it was before, it's going to be 4.9. So we're left with the 0.5s cancelling, we've got 35.6 add 4.9, which gives us 40.5 newtons at the bottom. So quite a significant change in tension. Okay, we were at 11 newtons while the mass was at the top, over 40 newtons at the bottom. So give or take a 4-fold increase in tension. Now that just figures for this particular example, doesn't always go up by the same factor. It would depend on a couple of different factors. Those factors being the speed, okay, at different locations. If we'd have had it going faster at the top, then that would have affected it, and also the radius of the circle that it's going in, because obviously that's then going to have an impact on the gravitational potential energy lost. Okay, now that is specific to our example. What we're going to have a little look at before we move on is just a bit of an extension, if you'll pardon a really poor pun. Okay, so we do an extension. Okay, I'm just going to have a little look at how this actually applies generally as we're going forward, so that you can see how the two tensions at the top and the bottom are always related. We've done a mathematical example just to see for that case how it's related, but there is a way of looking to see how they're always related to each other. So we can do that relatively straightforwardly if we go back to the idea of conservation of energy. So we've already said that half mv at the bottom squared was equal to half mv at the top squared plus mg delta h. Okay, we've already said delta h was 2r, so we're going to put that in. I will do that first so that you can see every step along the way. There. Okay, masses cancel, same as they did previously. I'm not going to cancel them though. Okay, I'm deliberately going to leave them in. Okay, you'll see why in a second. What I'm also going to do, simply because I know what's coming up, is I don't like the halves. Okay, so let's get rid of those. We're going to multiply the whole thing by 2. And at the same time, I'll do this in one step. I'm also going to divide the whole thing by r. Okay, it sounds like a strange thing just to do, but I'm just going to divide every bit by r. So I'm going to multiply each term by 2, divide each term by r at the same time. That will leave me with mv squared b over r equals mvt squared over r plus 4mg. Okay, that last term multiplied by 2 divided by r. Now, the reason I've done that hopefully will become a bit obvious now, because those are very familiar terms to us. Those are the centripetal forces at the two different points. And we've already established, if we go back to our diagram over here, that at the bottom, that is T at the bottom minus mg. And at the top, so that equals T plus mg plus 4mg. And all I'm going to do is add that mg to both sides. So I've got that mg added to that, so that's 2mg, add another 4, and I'm left with, sorry I missed the t off there for the top, that the tension at the bottom is the tension at the top plus 6mg. And that is true in all these scenarios for a mass on a string sort of case. It's not one that's on the formula sheet. Like I say, it is a little bit of an extension to go through, but you can see there is a set relationship between the two tensions going forward. Okay, now, hopefully not too confusing. Okay, what we're going to have a little look at now is a couple of special cases. Okay, we just looked at a scenario there where our speed at the top was 4 meters per second and it generated a speed at the bottom of 6 meters per second. Quite a significant increase. Okay, let's say an extra 50% on the speed going forward. What if our speed at the top had been 20 meters per second? How would that have affected things? And we didn't make any other changes as we go forward. Okay, well, we had v at the top, v at the bottom squared was equal to v at the top squared plus 2g delta h. Okay, that was an equation that we looked at when we had the earlier conservation of energy. That's what came out of that one. Okay, so it's just doing the same thing. Now, it is worth pointing out at this point, that looks very much like a Suvat equation. Okay, v squared equals u squared plus 2as. Okay, it does have the same format, the same dimensions. You must use conservation of energy here, not Suvat. It's really important. Suvat will give you the right answer for the wrong reason, so don't use it. Suvat, remember, is for linear motion. This isn't linear. Now, putting in the numbers again, just as we did before, to find the speed at the bottom, if the speed at the top was 20, well, that term's going to be 400. Okay, this term is 2g delta h. Delta h was 1 meter, so that's just 1. 2 times g is 19.6. So that gives us 419.6. And that comes out with a speed of about 20.5 meters per second, once you've square rooted that. So actually, if our speed at the top is much greater, so there's a much bigger kinetic energy at the top, at the bottom, we don't get a huge dramatic change. We've still got the same change in gravitational potential energy. That's not affected, but that's now a smaller proportion of the overall energy, which means that our actual energy change isn't too dramatic, so our speed change isn't too dramatic. And if the faster you go, or the smaller radius you have, so there's change in potential energy smaller, what you'll find is this will begin to approximate down to uniform circular motion. Okay, it will begin to approximate to it. It's not perfect, but the faster you go and the smaller radius, the closer you can consider it to being uniform, where the speed barely changes. Okay, we'll come back to that concept in a little bit, but that's just to highlight that point to you. Now, what is an important consideration with the mass on a string is something called the minimum speed condition. So I'm just going to sketch in our mass again. Okay, that was on our string, a radius of r. It was moving at a speed v that way, but actually was taking this circular path with omega. Okay, so that was the scenario we had. Now, when we looked at our centripetal force equation, so that was mv squared over r, at the top equals T plus mg. Now, if we rearrange that and we get T equals mv squared over r minus mg. There is a point here to consider that mg is constant for this mass. Okay, that's not going to change. But as v changes, the centripetal force required will change. Okay, and there will come a point, if centripetal force will usually be higher than mg, if it's maintaining circular motion, it'll have to be. But if we reduce the speed, so v decreases, then the centripetal force decreases. The effect that's going to have on the tension is the tension will actually decrease as well. If this term gets smaller, this stays the same, the tension will decrease. And there is actually a tipping point where the tension drops to 0. Okay, so when t equals 0, what actually happens is the string goes completely slack, and we actually completely lose our ability to have a centripetal force. Okay, because the only force we've now got acting, if t is 0, the only force we've now got, mg, is the weight. That always acts downwards. It doesn't change direction to match our centripetal, our circular motion parameters. So what will happen is once that's dropped to 0, once the tension drops to 0, this becomes a projectile rather than something moving in circular motion, where it's moving initially to, we've got it drawing to the right with a speed of v, and there is mg down. There's nothing else to pull it into place, so it will now just follow a parabolic path instead. Okay, if the tension drops to 0. That would be the actual scenario rather than following our nice neat circle. So at that point, it won't maintain circular motion. Doesn't mean it drops. This is a bit of a misconception. It doesn't automatically just drop straight downwards because it's got some horizontal speed. It follows projectile motion rather than circular motion. That's the key point there. Right, so when that happens, well, that happens when mv squared r over r equals mg. The centripetal force is equal to the weight, and there's therefore no tension. So if we just drop in that scenario, mv squared over r equals mg at that point, the masses cancel. So we're left with v squared equals r times g. So our minimum speed to maintain circular motion is actually given by the square root of rg. Just move that up because it's slightly off the screen there. Okay, so we've got a minimum velocity to maintain circular motion. Lower than that, we will lose the tension completely and it won't follow circular motion. Higher than that, we will gain some tension and it can keep going. Now, bear in mind what, of course, will happen as soon as it's higher than that, the tension will increase as it goes round and be at its maximum at the bottom. So if the string is going to break anywhere, it's most likely at the bottom. And of course, if it does break at the bottom, then again, we've lost our tension and it will follow a projectile path going forward. So that equation, okay, minimum speed is square root of rg, the minimum speed requirement to maintain circular motion in a vertical circle. It's really important. Again, not on the formula sheet. It's an absolute favourite of the multiple choice section of exam papers in particular. And you could sit there for your 1 mark and go through all those steps on that page and perhaps have some numbers to actually plug in, which takes a bit of time. Or you could bother to learn that little equation at the bottom and that will shortcut everything for you. You can just get on with the question, get it done really quickly. My advice that obviously there, learn that equation. The minimum speed at the top of this circle for a mass on a string is square root of rg. Right. I'm going to move on to looking at just discussing really the scenario that I mentioned earlier, which is we've got non-uniform motion for a mass on a string, but it's the easiest thing to sort of visualize, I think. So that's why I've gone with that first. We've seen that we can approximate it if the kinetic energy is high and the gravitational potential energy change is low. You can approximate even that to uniform circular motion. But this scenario can, of course, have true uniform circular motion. All you've got to do is think about an obvious example. For example, think of a wheel. Okay, if you think of a bicycle wheel, okay, we've not got two different parts of the wheel going at different linear and therefore different angular speeds. That wouldn't make sense. If the top of the wheel was going slower or faster than the bottom, the wheel would actually distort and deform shape, and that's no good. The whole rim has to be going at the same speed at the same time. There are fairground rides, Ferris wheels being an obvious example. There's lots of fairground rides where there's a unit going round in a uniform circular speed as well, angular speed. So it is achievable. And what we're just going to do is draw a quick diagram to have a look at how this is achieved so that you're aware of that moving forward. Okay, so here's our object. Okay, and it's going to be going at a uniform circle, a uniform circular motion with constant angular speed omega. Okay, and at various points throughout the cycle, so it's going to go this way round. That's a beautiful circle there. Okay, at various points, it's going to appear here, then here, then here, and it's obviously everywhere in between as well. Okay, now we can confidently say that we know what's going to happen at the top and the bottom. Nothing's going to change from the examples we've already looked at, where we've got weight downwards in both scenarios, and we've got tension downwards, but upwards there. Okay, we know that. And we know that the way to achieve that is simply to change the tension. That's really, really straightforward. So to achieve uniform circular motion, again, the tension just has to increase. It just won't be by the same factors that we've already looked at. So the tension will increase as we go down. No problems there. Where it gets interesting is actually when you look at these bits at the side. So we've got tension acting towards the centre. Okay. And we've got weight acting down. That's where our argument fell down before about maintaining circular motion, uniform circular motion particularly, because at these points the weight's downwards, the tension towards the centre. So simply what must be happening is this can only be a component of the tension. So we'll call it TH. But there must also therefore be a component of the tension, component of the tension that acts upwards, drawn the resultant in early, in those scenarios, that counters the weight. So something in these bodies that maintain uniform circular motion in a vertical plane must be able to provide not only a longitudinal tension towards the centre, but also a lateral tension. Okay, and I'm just going to draw that slightly larger from the side so that you can see what I'm talking about there. So again, here's our object. Okay. And it's essentially got two forces acting on it. And it's got mg. We've got tension that actually must be going off at an angle, so that the horizontal component, sorry, that's vertical. The vertical component is equal to mg, and the horizontal component is equal to mv squared over r to maintain our circular motion, giving us a resultant force in the horizontal direction of mv squared over r to maintain the circular motion. So just to recap, the weight is balanced by the vertical component of the tension, and the centripetal force is provided by the horizontal component of the tension. So there is a resultant force of mv squared over r only in this scenario. And now if you just think about the bodies that this could happen in, going back to our bike example, well, where does this lateral, the fancy word for it is a shear force, because it's acting across rather than along the body. Well, that's going to be provided along the spokes. That's why you've got spokes. They're all at different angles. They will have tensions in different directions. If it's a more rigid body, so a solid disc, obviously it's a little bit more easy to think about forces acting in different directions across it. It could be very much like our mass on a string example, except you replace the string with a solid body, a metal rod, for example, that will by and large hold its shape by allowing those tensions in different directions. So it is absolutely possible to have uniform motion in a uniform circular motion, in a vertical plane, just providing that you have some lateral tension components provided by in some way. Right, the last thing to look at is how these things look when we consider other objects. So we've looked at masses on strings and then applied that to some rigid bodies as well, where the tension can apply to keep things in uniform vertical motion. uniform vertical circular motion. There we go, got it right. Now the last example is just to look at some different scenarios. The last thing, they're not different theory-wise, they're just different scenarios that commonly come up, just to make sure you're familiar with a couple of these. And the first one I'm going to do is a loop-the-loop scenario. So instead of a mass on a string, we've got a circular vertical track with an object on it, so a roller coaster car, for example. At the top it's upside down, at the bottom it's the right way up, and we've got mv squared over r acting towards the centre at both points. And actually with this, okay, the forces involved is pretty much, well, it is exactly the same set of scenarios as we dealt with the mass on a string, where we have at both points weight downwards, and we've got another force providing the circular centripetal force, or contributing to the centripetal force, and that is just, instead of being a tension now, we'd call it a reaction force or a normal contact force. I've even just seen it called a push force occasionally. So the letters commonly used for this would be R, N, or even occasionally P. I'm going to stick with R for reaction for mine. So the reaction force would act downwards there and upwards there. Now remember, the reaction force, that's an upwards arrow, sorry. Remember, the reaction force is simply the push of the track on the car. Okay, if this was stationary at the bottom, then the car would be pushing on the track due to its weight, so the track pushes back on the car. So these are the forces on the car or the train or whatever you want to call it, and that's the reaction force. And obviously this is the, if you're a passenger in there, you're feeling the reaction force pushing against you. That's what you experience. That's what, we'll talk a little bit about weight in a second, but the experience of weight is, you don't experience the pull of gravity on you. You experience the push of the earth back against you, your reaction on the floor. That's what you feel, physically feel in these scenarios. So as you go round this track, exactly like the tension, it will have a smallest reaction force at the top, because it doesn't have to provide the whole centripetal force. The weight does some of it. At the bottom, it'll be the largest reaction force. So what you would experience as a passenger here is, because the reaction force is larger at the bottom, because it's got to overcome the weight of the car or the weight of you as a passenger, you will feel heavy because you are pushed down into, or well, technically the train is pushing up on you more, so you will feel heavier because of the bigger reaction force there. At the top, you'll feel bit lighter because of reduced reaction force there. And to maintain circular motion, exactly the same scenario that we had with the tension, there is a minimum speed requirement. Okay, and it is exactly the same equation. Okay, you can work through it if you want to prove that to yourself, but as you can see, all we've simply done here is replace T for tension with R, so the equation works the same. So there's a minimum speed to maintain circular motion. Okay, we're just going to finish looking at a scenario of a humpback bridge, is the classic one, with a car going over a humpback bridge. This would also apply to a train at the top of a roller coaster curve, or an aircraft climbing and topping out and then going into a dive. Any scenario similar to that. And of course we've got, so just sticking with the car on the humpback bridge example, we've got its weight, mg downwards, and we've got a reaction force of the car on the road upwards at any given point. And so the centripetal force towards the centre of this, assuming that this path is then circular, is mv squared over r, is mg. We're going to take down as positive now because that's the direction of the centripetal force. Subtract r. If we rearrange that to get it in terms of r, so r equals mg minus mv squared over r. Now mg is constant, so v can vary. M and r, they're going to be constant. And what we can see from this equation is, as v increases, r actually decreases. Okay, and what we can do from that is say, well, what happens when v gets to such a point that mv squared over r equals mg, so that r actually drops to 0. So mv squared over r equals mg, therefore r is 0. Okay, and look at what happens with that scenario. Now that's happening because v is increased. So that will give us an equation to have a look at. So let's just see where that leads us. So m's cancel here. We've got v squared over r equals mg. So that rearranges as so. And we end up with that equation again. Okay, v equals root rg. Now, the only difference being that this time, that is a maximum, not a minimum speed. We've had v increasing. As soon as it hits that point, r is 0. And what will happen to the vehicle is it's lost, that means it's lost contact with the road. Now, here's where the misconception quite often comes in with this one, and we'll address another one as well at the same time. There's a bit of a misconception here that if the car's lost contact with the road, then essentially it's become airborne. And the misconception here is the idea that if we remove an upwards force, how does it move upwards and leave the road? It hasn't done that. What's happened is we've got to a scenario where forget r for a second, that's the important thing here, forget r. mv squared over r is provided by mg. If velocity gets too big, the weight is unable to provide the centripetal force. It's not big enough to provide the required centripetal force, and that happens at this point. It just so happens that at that point, that means that r has become 0, because that is the definition of when it's left the road. When the reaction force is 0 means it's left the road. So by definition, it's left the road, and because there's no reaction force, essentially the car therefore is weightless, or the passengers in it would experience weightlessness because they've got no reaction force of the earth pushing up against them. So that's the key thing. R has dropped to 0, and that's not what's caused it to leave the ground. That's a consequence of it leaving the ground, and it's left the ground because mg, the weight, is no longer large enough to provide the centripetal force there. And it's a very similar scenario with our tension of the string example that we had earlier. When the tension dropped to 0, it was no longer able to provide the centripetal force. It's not that removing that downwards force causes it to drop, because that would be counterintuitive. It's that the centripetal force is no longer able to be provided by the forces that are there. Okay, hopefully that will clear up that little misconception which before it even arises. But that concludes this little sort of section. Hope it's been useful, and as usual, any questions, please do get in touch.